Welcome to all of you. This is Naren Sharma, Government First Aid College, Vartur. Here I am continuing my discussion on quantum mechanics part 2, which belongs to 6th semester BSc physics course. So this is my 5th session. So today I want to discuss one of the application of Schrodinger's time independent equation. That is particle in a one-dimensional box. We can apply Schrodinger's time independent equation to variety of problems. So today we are discussing one such application. So let us briefly discuss about the objectives of this particular session. This is the 5th session. As I have told, we want to apply Schrodinger's equation to a particle in a box. We shall try to understand what is the meaning of a box. Box means it is a potential energy box. So we are going to apply the Schrodinger's equation to a particle in a one-dimensional box. And while solving this equation, we will come to know about several things. For example, we will come to know about energy eigenvalues of the particle in the one-dimensional box. So therefore, we are going to derive an expression for the energy eigenvalues of particle, which is situated in a one-dimensional potential box. Not only energy eigenvalues, we are also going to find out the wave functions of the particle. Essentially, they are called energy eigenfunctions. So we are going to find out expression for the wave function of the particle in a box. And of course, we also try to plot those wave functions as a function of the distance along x-axis. So therefore, the third objective is to plot the wave function of the particle in the box. Therefore, we should try to understand the behavior of the wave function and of course probability density inside the box, one-dimensional box. And this example actually gives a very beautiful example for quantization, what we call it as quantization. The energy eigenvalues are quantized. So the energy of the particle inside the box cannot take equal to the set of values. It can take only some discrete set of values. That is what we call it as quantization. And this is one such phenomenon. So for quantization, in which the energy of the particle can take only some discrete set of values. So therefore, this is our last objective. So we need to understand the quantization phenomenon also. So these are the 4 objectives. So overall, we are going to apply Schrodinger's equation to a particle in a box, and we try to solve the differential equation. Therefore, we end up with several eigenfunctions, energy eigenfunctions, as well as energy eigenvalues. So through this, we shall also try to understand the meaning of quantization. So let us begin now. So this is one of the application of Schrodinger's time independent equation. So the case is particle in a box. It is one-dimensional case. So I have shown a diagram here. So this is the diagram for the graphical representation of the potential box. So here along x-axis, this is the x-axis, and this is y-axis. Along x-axis, we have taken the x coordinate itself, and along y-axis, we have taken the potential energy of the particle. So we have a region x is equal to 0 and x is equal to L. So within this particular region, beyond this particular region, for example, for the values of x lesser than 0 and for the values of x greater than L, so the potential energy is infinite, so that the particle which we are considering right now, which has a particle of, which has a mass of m, so it is actually restricted to travel between these two walls, these two boundaries, x is equal to 0 and x is equal to L. So the particle cannot exist outside, basically because the potential energy of the particle outside these two boundaries is infinitely large. So therefore, particle cannot have infinite potential energy. So therefore, we conclude that the particle cannot exist beyond x is equal to L region and beyond x is equal to 0 region also. So therefore, this is a case where we have a particle having mass m, which is restricted to travel or move within these two boundaries, x is equal to 0 and x is equal to L. Now, the particle's potential energy inside this particular region is constant, okay? And compared to the potential energy of the particle outside, which is, the particle cannot exist outside because the potential outside the region is infinite. So we can assume that the potential energy of the particle particle inside this particular region as 0. So therefore, our discussion, we can assume that the particle is trapped between two regions, x is equal to 0 and x is equal to L. The potential energy of the particle inside this particular region is 0, and the potential outside these two regions is infinitely large. So therefore, essentially we assume that the particle cannot exist outside this particular box, potential box, or it is also called as a potential band. So our particle is trapped in the potential band. It cannot go outside because so potential energy is infinity. That is not possible. So therefore, for our purposes, we can assume that the potential energy of the particle within this particular region as 0. So this is an example. This region is an example for one-dimensional rectangular potential box. So we need to understand what is the behavior of the particle, so which is trapped inside this region because of this one-dimensional rectangular potential box. So in order to do this, we shall try to apply Schrodinger's equation for such a particle. Now Schrodinger's time-independent equation for one dimension is given by. So in one of my previous session, so we have already found out the expression for Schrodinger's equation, time-independent equation for one dimension. So therefore, the equation is given by d square psi divided by dx square plus 2m by h cross square E minus V of psi is equal to 0. This is the general form of the Schrodinger's equation, time-independent equation 1. Now, for this particular case, as we are discussing here, in this particular case, the potential energy of the particle inside the boundary, inside the box, is 0. So therefore, so I can say that. So we can substitute V is equal to 0 in this equation 1. If we substitute V is equal to 0 for this present case, so the Schrodinger's equation actually becomes d square psi divided by dx square plus 2me divided by h cross square psi is equal to 0. This is what the form of the Schrodinger's equation of the particle, which is trapped inside one-dimensional potential box, where we are assuming the potential energy of the particle to be 0. So as I have mentioned, the particle cannot exist outside the box. It has to be inside the box itself, potential box itself. So therefore, we can put certain restrictions on the wave function of the particle. So therefore, wave function satisfies certain conditions, boundary conditions. And those boundary conditions are the wave function of the particle must be 0 for the region x less than or equal to 0. I have already told the particle cannot exist beyond the region x is equal to 0 on the left side of the diagram. So therefore, the wave function of the particle must be 0. Similarly, the particle cannot also exist outside the region x is equal to L. So therefore, we have the second boundary condition, psi must be 0 for x is greater than or equal to 0. So these two are called boundary conditions. These two boundary conditions give us the idea that the particle cannot exist outside the potential box. So we shall make use of these two boundary conditions, equation 3 and 4. Now this equation 2 can be written as, for simplification purpose, we can write this expression as d square psi divided by dx square plus k square psi is equal to 0, where we have chosen so 2me by h cross square as k square. So therefore, if we substitute, then we are going to end up with the equation d square psi divided by dx square plus k square psi is equal to 0, equation 5. Now this equation 5 is a linear second order differential equation, and this linear second order differential equation has a standard solution. We are not discussing about all this how to obtain the solutions in detail. I have written the general solution of this equation 5 directly. So therefore, we can say that so the equation 5 has the general solution given by psi of x is equal to a sin kx plus b cos kx, where a and b are some constants which we need to find out. K is as usual, k square value is 2me by h cross square. So therefore, k becomes equal to square root of 2me by h cross square. That is a very simple thing. Now we are going to use the boundary condition. The first boundary condition I have told psi is equal to 0 for x is e less than or equal to 0. I am going to use psi is equal to 0 for x is equal to 0. So if we use that boundary condition, so then equation 3, first boundary condition, so then we are going to get b is equal to 0. So here in this equation, if you substitute, so psi is equal to 0. So for x is equal to 0, so then a into sine of 0, if If you substitute x is equal to 0 here, sine 0 is 0. So therefore, this whole term vanishes, and b into cos of 0 is 1. So on the left side, we have psi is equal to 0. So therefore, which gives us one small information that b is equal to 0. So therefore, what we can prove that using the first boundary condition that the value of b is 0. So therefore, if we substitute the condition b is equal to 0 in the equation 6, we are going to get the equation psi of x is equal to a sin kx. A simple mathematical thing that anybody can do. Now I'm going to use the second boundary condition. Please observe the second boundary condition. Psi is equal to 0 for x is equal to L greater than also we can use. But anyhow, for the present situation, we have to use it. Psi is equal to 0 for x is equal to L. If you substitute this equation 4, so the second boundary condition, and if you substitute in this equation 7, so psi is equal to 0 for, so k becoming equal to L. So then in the respective case, we are going to get psi a of sin kx is equal to 0. So which implies that sin kx is equal to 0. And since x is equal to L, we can substitute in the place of x, we can substitute L. So therefore, we are going to get kn. Sin of kx is equal to 0 or sin of kl is equal to 0 implies that the general solution we are going to get is n pi. So therefore, the value of k that we are going to get here is n pi by L. So therefore, we can conclude that using the second equation, using the second boundary condition, we get another condition that the value of k into L must be equal to n pi, or the value of k must be equal to n pi by L. So this is equation 9, where n is an integer and it can take only discrete set of values 1, 2, 3, 4, 5, and n is what we call it as quantum number of the particle. Here, n is given the name quantum number, and it can take discrete set of values 1, 2, 3, 4, 5, etc., etc., etc. Okay. So if we substitute this equation 9 in our original solution, the original solution is, let me show here, the original solution is psi of x is equal to a into sin kx. So if we substitute the value of k here, so I'm using equation 9 in equation 7, then we are going to get the solution psi of x is equal to a into sin of n pi by L into x. So equation 10. So this equation 10 is the solution of our equation, showing us equation for the particle in the one-dimensional box. We have substituted x as n pi by L. So n is nothing but quantum number, and it can take discrete set of values 1, 2, 3, and L is what we call it as length of the potential box, that's the size of the potential box. So x is as usual x coordinate. Okay. So this is equation 10. Equation 10 is the solution of the equation. This equation 10 is again incomplete in the sense the value of a, another constant we don't know yet, and we need to find out. In order to find out this constant a, so we need to do normalization. Once we are able to normalize the wave function, which is represented by equation 10, so definitely it is possible to find out the value of a, and this whole process is what we call it as normalization. So therefore, to find out the value of a, we normalize the wave function represented by equation 10. So the normalization says that, so since a particle can exist within the two walls, two boundaries of the potential box, so therefore the particle has to exist anywhere inside the box. It cannot exist outside the box, but anyhow it has to exist anywhere inside the box. So therefore the total probability of finding the particle anywhere inside the box is 1, and therefore mathematically that condition 0 to integral 0 to L psi star of psi into dx, which is also equal to integral 0 to L modulus of psi square into dx must be equal to 1. So this gives the total probability of finding the particle within the box. So that's why we have the limit x is equal to 0 and x is equal to L. X is equal to 0 to x is equal to L covers the entire box. So therefore the total probability of finding the particle anywhere inside the box is 1. And such a condition is what we call it as normalization condition. So therefore the normalization condition can be written as integral 0 to L modulus of psi square dx into 1. So here psi is something like for real function, it doesn't have any constant, complex constants. So therefore, in order to simplify, in order to get this equation, what we can do is we can square this equation. If we square this equation 10, we are going to get a square into sine square of n pi by L into x. So therefore, after squaring, I can substitute in equation 10. So therefore, I'm going to get a square is constant. So therefore, I can take it outside. Then integral 0 to L sine square of n pi by L into x dx. n pi by L x into dx is equal to 1. This is a simple differentiation, simple integration process. Once we do this simple integration process, and after simplification, we are going to get a value of A as 2 by L whole to the power of 1 by 2. So therefore, we can conclude that the value of A normalization constant comes out to be something like this: 2 by L whole to the power of 1 by 2, or square root of 2 by L. That is what the value of normalization constant A. So therefore, once you substitute the value of A, the normalization constant, back in the equation, then we get a normalized wave function for the particle in the rectangular potential bars. So therefore, the normalized wave function for the particle inside the box is now given by psi of x is equal to 2 by L whole to the power of 1 by 2 sine of n pi by L into x. So this above expression can also be written as, so psi of n, please observe here, this particular equation psi wave function is a function of n quantum number. If n keeps on changing, psi also changes. So in general, this is what we written as a psi of n. In order to denote the state, the quantum state also, so we write subscript n for psi. So therefore, psi of n can be written as, so 2 by L whole to the power of 1 by 2 sine of n pi by L into x. So equation 11. So this equation 11 represents wave function of the particle inside the potential box. These wave functions are also called as energy eigenfunctions. So what we are able to do is, we are able to find out an expression for energy eigenvalues of the particle which is trapped inside one-dimensional rectangular potential box. So they are completely normalized because we have found out the normalization constant. So therefore, we are able to find out the equation in this particular fashion, equation 11. Okay. So this n is what we call it as a quantum number, and the n value actually corresponds to different quantum state. For example, if we substitute n is equal to 1 here, then we are going to get psi 1. So psi 1 is corresponding to n is equal to 1, and that is what is called as the ground state of the particle inside the box. And if you substitute n is equal to 2, then we are going to get psi 2 is equal to 2 by L whole to the power of 1 by 2 sine of 2 pi by L into x, and that is called the wave function in the first excited state. And if you substitute n is equal to 3, then we are going to get, so is psi 3. Psi 3 is equal to 2 by L whole to the power of 1 by 2 sine of 3 pi by L into x. That actually gives the wave function of the particle in the second excited state. N is equal to 1 is called the ground state. N is equal to 2, 3, 4, 5, 6, 7, 8, etc., etc. They are called excited states. For example, n is equal to 2 is called first excited state. N is equal to 3 is called a second excited states, and so on. So therefore, we are able to find out expression for the energy eigenfunction or the wave function of the particle inside the box. Now, it is also possible to find out energy eigenvalues. So the value of k we have found out, n pi by L, and also we had written expression for k square as 2mE by h cross square. So we can combine these two equations. I can square this particular equation and I can compare with this equation. After doing this comparison and simplification, we are going to get expression for energy of the particle inside the box as E is equal to pi h cross square n square divided by 2mL square. So E is nothing but energy of the particle inside the box. Now, clearly, according to this particular equation, E is a function of n, the principal quantum number. So therefore, we don't write E, we write it as E subscript n. So E subscript n, En is equal to pi h cross square n square divided by 2mL square. So this expression, equation 12, gives the possible energy values of the particle inside the potential box, one-dimensional potential box. So therefore, these energy values, so given by equation 12, they actually give energy eigenvalues of the particle inside the box. For example, if I substitute n is equal to 1 here, then I am going to get E1. E1 is the energy of the particle, as I mentioned earlier, or the ground state, because n is equal to 1 corresponds to ground state. If I substitute n is equal to 2 here, then I'm going to get the value E2, and E2 is nothing but energy of the particle in the first excited state. Second state, it is called simply second state, or it is also nothing but first excited state. If I substitute n is equal to 3 here, then I'm going to get, so E3. E3 is nothing but energy of the particle in the third state. The third state, n is equal to 3, is also nothing but a second excited state, because n is equal to 1 is called the ground state. So therefore, this expression, the last expression, equation 12, so denotes the possible energy values of the particle inside the box. So therefore, they are called energy eigenvalues of the particle in the one-dimensional potential box. So therefore, by simply applying Schrodinger's equation for a particle in a one-dimensional potential box, we are able to find out two different expressions. One is the expression for the wave function psi n, which is given by normalized wave function, which is given by psi n is equal to 2 by L to the power 1 by 2 sine of n pi by Lx, sine of n pi by L into x, equation 11. So this expression gives energy eigenfunctions, and equation 12, En is equal to pi square h cross square n square divided by 2ml square. So it's nothing but the possible energy values of the particle inside the box. So this expression is what we call it as energy eigenvalue expression. So therefore, we are able to derive an expression for energy eigenfunction and energy eigenvalues of the particle in a one-dimensional box. Okay, these are the two things we wanted to derive, and we have successfully derived these two expressions. Now let us proceed further. Let us try to understand the graphical representation of wave functions and their probability densities. So as I have mentioned earlier, so according to equation 11, the wave function is given by 2 by L 1 by 2 into sine of n pi by Lx into n pi by L into x. So this whole function can be plotted as a function of x for different values of n. And if I take modulus, so square of this one, modulus of the square of this particular thing, modulus of the square of the wave function actually gives the probability density. So therefore, it is also possible to find out two different graphs. One is the graph for the wave function, another one is the graph for modulus of psi square. Modulus of psi square is nothing but the probability density. Okay, so therefore, these are some of the graphs. So in which the normalized wave function psi1, psi2, psi3 together with their respective probability densities. That means for the first state wave function psi1, the probability density is modulus of psi1 square. For the second state, if the wave function is psi2, its probability density curve is modulus of psi2 square, and so on. So it has been done for three different cases: for n is equal to 1, for n is equal to 2, and for n is equal to 3. Let us discuss them one by one. So here we have the two boundary. We know that the particle is existing between the two boundaries, x is equal to 0 and x is equal to 1. So this left side represents the graph of psi1, psi2, psi3, and the right side three different curves. Actually, they represent their respective probability densities: psi1 square, psi2 square, and psi3 square. Let us discuss one by one. In both the diagram, x is equal to 0 and x is equal to L represent the two extremes, the two walls of the potential box, within which itself our particle can exist as per our initial assumption. So here, this is the graph corresponding to n is equal to 1. So therefore, it's a graph of psi1. So according to this particular graph, wave function is vanishing at x is equal to 0 and x is equal to L. The particle cannot exist even at the boundaries. It cannot exist outside the boundary also, and it cannot exist at the boundary also. So therefore, the value of psi1 is 0, 0 at two extremes, x is equal to 0 and x is equal to L. And as I move from x is equal to 0 to x is equal to L region, so the wave function keeps on increasing, and it actually becomes maximum at the middle in the sense x is equal to L by 2, and then again it falls. So this is how the wave function changes inside the box for n is equal to 1 state, that is the ground state. And if we write the probability, so then the probability of finding the particle inside the box for n is equal to 1 state more or less varies in the same fashion as the wave function. So therefore, the probability of finding the particle at x is equal to 0 and probability of finding the particle at x is equal to L is 0. Anyhow, as we move from x is equal to 0 to x is equal to L, so probability keeps on increases, and the probability becomes maximum exactly halfway, that is x is equal to L by 2. And again, as we move from halfway region to the end region, x is equal to L, again the probability falls. So therefore, according to this particular graph, so the probability of finding the particle would be maximum exactly at the middle of the box. At the middle of the box, so the probability of finding the particle is maximum for the ground state, that is for n is equal to 1. So therefore, this particular place for the ground state where n is equal to 1 and the probability is maximum at the center. So this particular place where the probability is maximum is what we call it as antinode. So therefore, we have one antinode here. We have one antinode here at the middle point. And the probability of finding is finding the particle at the two extreme positions x is equal to 0 and x is equal to L is 0 at the two extremes. So therefore, we have two antinodes. So for the case n is equal to 1 at the ground state, so we have one antinode and two nodes. Antinodes are the points where the probability of finding the particle is maximum. So nodes are the points where the probability of finding the particle is 0. We cannot find the particle at the two extremes, so therefore we have two nodes. One is at x is equal to 0 and another one is at x is equal to L. And we have one antinode because exactly at the halfway, exactly through the halfway, so the probability of finding the particle is maximum. So therefore that actually corresponds to antinode. This whole discussion is actually applicable for n is equal to 1 case. Similarly, if we go to n is equal to 2 case, in the case of n is equal to 2, if we plot a graph, okay, for example, in the expression 11, if I substitute psi 2, so then I'm going to get 2 by L to the power of 1 by 2 sine of 2 pi by L into x. And if we keep on changing the value of x from x is equal to 0 to x is equal to L continuously, then we are going to get this particular graph. So this is a simple sine graph where the value of the wave function again is 0 at two extreme positions, and again it is 0 in the middle way, and there is a maximum value at this particular place and at this particular place. So this actually corresponds to 1/4 of the distance from this end, and this portion also this region also corresponds to 1/4 of the distance from the other extreme. So we have a different situation here. So the wave function is 0 at two extremes. Not only that one, the wave function is 0 at the middle way, unlike the previous case where the value of the wave function was maximum at some middle way, halfway. So here at 1/4 of the distance from either sides, so the value of the wave function is maximum. So and at the three places, x is equal to 0, x is equal to L, and x is equal to L by 2. So the value of the wave function is 0. And if we plot the respective probability density, that means if we take the function psi 2 and modulus and then take the square, and if we plot the graph, so the graph would be something like this. So according to this particular graph, the probability of finding the particle at this particular place x is equal to 0 is again 0, and probability of finding the particle at x is equal to L is again 0. And not only the probability of finding the particle midway, halfway, is also 0. So therefore here, corresponding to n is equal to 2, we have three different places at which probability of finding the particle is 0. One is at x is equal to 0, another one is at x is equal to L by 2, another one is at x is equal to L itself. So at the three different places, so the probability of finding the particle is 0. So therefore we have three nodes here corresponding to the first excited state, n is equal to 2. Whereas if I go for 1/4 of the distance, 1/4 of the distance from x is equal to 0, or 1/4 of the distance from x is equal to L, again the probability of finding the particle is maximum here. So at two different places, so the probability of finding the particle is maximum. So therefore, unlike the previous case where the probability was maximum halfway, now probability of finding the particle halfway corresponding to n is equal to 2 state or the first excited state is 0, whereas the probability becomes maximum at x is equal to L by 4 as well as x is equal to 3L by 4. So therefore we can conclude that corresponding to n is equal to 2, the first excited state of the particle inside the box, we have three nodes, one first node, second node, third node. Whereas we have two antinodes, so two antinodes where the probability of finding the particle is maximum. So similarly, we can do the same type of discussion for n is equal to 3 also. I'm not going to discuss n is equal to 3 case in detail. It is shown explicitly in the graph. So here we have 1, 2, 3, 4. So there are at 4 different places. or we can see the probability density curve itself. So first point, the second point, third point, and fourth point. At 4 different points, the probability of finding the particle is 0. So therefore, we have 4 nodes, and the probability of finding the particle is maximum at the 3 different places. At this particular place, at this particular place, and at this particular place. So therefore, we have 3 antinoods. So this is how we can understand the behavior of the particles wave function as well as the probability densities of a particle which is situated inside the potential one-dimensional potential box. The same thing explanation is given here. So anyhow, here I'm going to end my session. So this what actually completes our discussion on one of the application of the Schrodinger's equation. So one-dimensional case. So to a particle trapped in an infinitely large potential box, rectangular potential box. So we applied the equation. We could solve the equation, and after solving the equation, you could actually find out the wave function, solution for wave function, and solution for energies. So the wave function solutions are called energy eigenfunction, and energy solutions are called energy eigenvalues, and therefore we are able to represent them graphically also for three different states: n is equal to 1, n is equal to 2, and n is equal to 3. So this is what the first application, and we want to discuss the second application, a particle which is trapped in a three-dimensional box. We shall continue in the next session. Anyhow, I am going to stop this particular session, and I am thanking you all. Thank you.